Hello, welcome to Zigmatech Learning Hub. I will be your instructor for chemistry. For this class, we are going to be taking our exercises from the Examguide app. If you don't have the application already installed on your device or on your phone, I will want you to download the app in order to follow along in this class. Examguide is a leading educational app that helps students prepare adequately for various exams like UTME, post-UTME, WEAC, JCE, KCPE, IJMB, JUPEB, Calbepedia, BECE, JSCE, NCEE, NECO, etc. You can download the app from www.examguide.com or Google Play Store. Please subscribe to our channel and turn on the notification bell to be updated on new videos. Ready for today's class? Okay, let's get started. Now, welcome again, once again, and again and again. In this particular lesson, we're talking about the Charles law, the gas laws 2. Gas laws 2. Remember, we talked about the gas laws part 1, where we talked about the Boyle's law, the Charles law, and the Avogadro'S law. But in this particular section, we'll talk about the other laws that made up the gas laws. But before then, we are going to look into the graphic explanation of Charles' law. I didn't tell you that. And Avogadro's law. I didn't draw it for you. Before I start this section, I'm going to draw this, the Avogadro's law, the Charles' law graphically, and the Avogadro's law graphically. Now, this is the Charles' law graphically. Okay, that's the Charles law graphically. Now, this is the volume. This is the temperature. And this is the pressure constant. Charles law. And this graph is called isobar. This graph is called isobar. As you can see, the graph is called isobar. So, as you can see, as the pressure is increasing, the temperature is increasing, and the volume is increasing. As the pressure is increasing, the temperature is increasing, and the volume is increasing. In essence, it is V divided by T all over K. The volume divided by the temperature gives me the constant. That is proportional. So if I want to look for T, it will be K divided by V. If I want to look for V, it will be K. And you can still say V equals to K over T. V equals to K over T. Any which one you like, you use. We know that the Charles law, is P1. We know that the Charles law is V1 all over T1 equals to V2 all over T2. So this is the graph of the Charles law, and it's called isobar. Isobar. As the pressure is increasing, the temperature is increasing, the volume will do what? Increasing. So this is the graphical expression. So the formula you can see the V over T equals to K, or V equals to K over T. Now, let's look at the Avogadro's law. Avogadro's law. The graphical representation of Avogadro's law. The graph of Avogadro's law. The graph of Avogadro's law. Now, it's a simple thing. This is the graph of Avogadro's law. Here is the number of moles. Okay? Here is the number of moles, and here is the volume. Remember, it said equal volume of gases has the same number of molecules. Okay? Calculate number of molecules. So here is the slope constant. Here is the slope constant. We have Vn is equals to K. In essence, when they are constant, the number of molecules is the same. When they are constant, the number of molecules is are the same. So this is the graph representation of Avogadro's constant, or Avogadro's law, or Avogadro's hypothesis. Anyway, you want to call it, you call it Avogadro. Okay, so this is how the Avogadro's law is being represented graphically. Okay, now let us go into what we want for today, the business of today. Okay, now the business of today is the gas laws part 2. So by the end of this lesson, you should know the Gay-Lussac's law of combining volumes and how to solve problems using the law. The Dalton's law of partial pressure, the combined general and ideal gas laws and equation. The Gay-Lussac's law of combining volumes and how to solve problems using the law. The Dalton's law of partial pressure, the combined general and ideal gas laws and the equation. Now the first one is the Gay-Lussac's law of combining volume. The Gay-Lussac's law, still known as the law of combining volumes. Okay? It tells us about atoms combined. How are the atoms combined together in ratios? How the atoms combined together in ratios. He brought out this law in 1808, from 1802 to 1808. That's when the law came out. He combined volumes using hydrogen and oxygen in formation of water. Now, when he formed hydrogen and oxygen and he gave us water, he came to realize that the ratios, the combining volumes of the ratios came to give us in the same ratio. All of them came together and gave us one ratio. So, in this context, let's take for example, now you have A plus B equal to C. Okay, these are the elements A, B, and C. The ratio will be A is to B is to C. Simple. A is to B is to C. All of them give us one thing. Okay, this is just the ratio of atoms combined. That's what Gay-Lussac's law is telling us about. Now let's look at Gay-Lussac's law. Gay-Lussac's law says when gases react, they do so in volumes which bear a simple whole number ratio to another, and to the product formed if gaseous, provided the temperature and pressure remains constant. As you can see, before and after. Before, all of them were together. After the reaction, they still became together. Their ratio did not change, even in the product. As you can see, I said A, B, and C. This A represents the subscripts of this A, B, and C, the element. The C is the product. Okay? They became the whole number ratio. The whole number ratio. H. Now, this is 2:1. Okay? They gave us the whole number ratio, which is 1. Both of them came together and gave us 1. 2:1 gave us 1. Whole number. They did not give us 2:1 again here. They gave us a molecule of water. Okay, so this is what it's telling us about the atoms combined in giving us a whole number ratio. That's what the Avogadro's law, the Gay-Lussac's law of combining volumes is telling us. That when you combine volumes together, they'll become one thing. Okay, it's like you bring hydrogen and oxygen together, they'll give you one thing, which is water. They will not separate. Their ratios, their numbers, this is 2 atoms. Okay, and 1 atom gave us one thing again, 1 molecule. 2 molecules plus 1, and reacting with 1 molecule gave us 1 molecule. 1 thing again. They did not scatter. So their ratio became a whole number ratio. Now mathematically, it's P1 divided by T1 at constant temperature and pressure. If the temperature and pressure is constant, they are going to give you the same thing. I'll just give you an example of this. Okay, give me an example of this. Now he said form if gaseous. If gaseous. Now if gaseous, let's take two gases. Oxygen and hydrogen will give us hydroxide. Still one whole number ratio. The same thing. So mathematically, we said the first pressure, which is P1 divided by T1 equals to P2 divided by T2. Where P is the first pressure, T1 is the first temperature, P2 is the second pressure, and T2 is the second temperature. Now let's take a question from Avogadro's law, Avogadro's constant. From Gay-Lussac's law. Let's take a question from Gay-Lussac's law, Gay-Lussac's law. They say consider the reaction. 2 molecules of hydrogen and 2 atoms of oxygen gave us steam, gas. In essence, the state of matter of hydrogen is gas, state of matter of oxygen is gas, and state of water is gas. Now they say consider the relation and say what volume of steam is formed from 20 centimeter cube of hydrogen and 20 centimeter cube of oxygen mixed together. What volume of steam is formed? Okay, they've given us the volume of hydrogen, which is 20, given us a volume of oxygen, which is 20. Now, how do we know the volume of water as the steam? Now, if you check, the ratio there is 2:1:2. 2:1:2. I just gave you a similar analysis of A, B, and C. Okay, the hydrogen there is 2. The oxygen molecule there is 1, and the water there is 2. Look at the letters, the numbers, the big numbers. That's what you look. The small numbers are just the number of atoms, they are subscript. Okay, you do not look at the subscript, you look at the number of molecules. I told you, if a number is written together with an element, it is a molecule. So look at the number of the molecule. So the number of the molecule, the hydrogen there is 2:1:2. If you check it very well, you see there. 2:1:2. The hydrogen is 2, oxygen is 1, and water is 2. Now, this is the ratio 2:1:2. Okay. Now, how do we get a normal ratio? These two. How do we get a normal ratio now? They say what volume of steam is formed from 20 centimeter cube. In essence, hydrogen is equal to 20 centimeter cube. And its ratio is 2. Oxygen is how many? 20 centimeter cube, 2. And its ratio is 1. Okay? Now, this 20, ratio means divide. When they say ratio means what? Divide. In essence, this 20 will divide the subscript, which is 2, times the molecule, which is 1. This ratio will divide the subscript, which is 2, times the molecule, which is 2. In essence, if I use 20 and divide the ratio of 2, it will give me 10. In the hydrogen will be equal to 20 divided by 2, which is the ratio. This is the ratio of which we get 2, times the molecule of the hydrogen, which is 2. Remember, hydrogen molecule, this is 2. Let me give 2H. Times the hydrogen molecule, which is 2. So if I divide it now, it will give me 20 divided by 2 is 10. 10 times 2 is 20. Now we've gotten the ratio of hydrogen as 20. Now let's get the ratio of oxygen. Ratio of oxygen. This is ratio of hydrogen now. Ratio of oxygen. Of O. Ratio of oxygen. Oxygen is 20. Okay? Oxygen is 20. Now the ratio is how many? 1. Divided by 1 times the subscript, which is what? 2. Okay, the ratio is 20 divided by the subscript, 2, times the molecule, which is 1. So 20 times divided by 2 is 10. 10 times 1 is 10. So we've gotten the ratio of oxygen, which is 10. The ratio of oxygen is 10. Now, if you check the steam comprises of oxygen and hydrogen. Oxygen and hydrogen. Okay? Oxygen and the hydrogen. So oxygen there is 20. Hydrogen is 10. Oxygen is 20, hydrogen is 10. In essence, ratio of steam is equals to the hydrogen minus the oxygen. Remember, the positive sign will change to minus. Positive sign there change to what? Minus. So it will be the H minus O, which is equals to 20, which is equals to 20 minus 10. So if you check this constructively, you know that the steam is 20. The steam becomes 20. In essence, the ratio of this particular thing, the steam 20 minus 10, sorry, it will be hydrogen minus oxygen. Sorry to say, hydrogen minus oxygen times the number of molecules. Times the number of molecules. So hydrogen minus oxygen is 20 divided by, is 20 minus 10, which is equals to 10, times 2. Because the steam there is 2. In essence, ratio of steam is equal to, therefore, ratio of steam is equal to what? 20. Are you following? Yes. Ratio of steam is equal to what? 20. So the ratio now is 2:1:2 has changed to 20:10:20. The ratio has changed as 20:10:20. Now, look at this constructively, like I said. The ratio of hydrogen. Okay, they say what volume? The volume of hydrogen is 20. And the ratio is 2. Because we say 2:1:2. Hydrogen is 2, oxygen is 1, and steam is 2. Check their molecules. 2:1:2. Now the ratio of the volume of oxygen is 20. The ratio is 2. The volume of oxygen is 20. The ratio is 1. Volume of hydrogen is 20. Sorry, the ratio is 2. Oxygen is 20 and the ratio is 1. Now to check the ratio constructively, you have to divide the subscript, which is 2. There's a small 2 there. There 2 is a subscript. If you follow up, you know what the subscript is. I told you that any number at the base of an element represents the subscript and its number of atoms in that element. But if the one that's written together with the element represents the molecule, number of molecules. So now, the hydrogen has 20 already as a volume, divided by the subscript, the number of atoms, times the number of molecules. So the number of atoms there is 2, and the number of molecules is 2. So it will be 20 times 2, 20 divided by 2 times 2, which is 20. That's the ratio now. For oxygen, ratio of oxygen, the volume is 20. The number of atoms there is 2, that's small 2. And the molecule there is 1, oxygen 1, which is 10. Now, it gave us a product which is steam. It gave us a product which is steam. Now, the steam will be the hydrogen, first one, minus the oxygen. Because the plus sign will change to minus. In essence, the hydrogen will minus the oxygen, times the molecule, which is 2. That molecule there is 2. The molecule of steam there is 2. Now, when you times it, when you divide it with 20 divided by 10, which is 10, 10 times 2 is 20. As you can see, we'll be going further. Follow up, we'll be going further. Okay? Now, the ratio now, in essence, they say what volume of steam is formed from 20 centimeter cube of hydrogen and 20 centimeter cube of oxygen mixed together. What volume? In essence, it is 20 ratio 10 ratio 20. 20 ratio 10 ratio 20. So in essence, the first answer is 20 centimeter cube. Answer 1. Is 20 centimeter cube of steam formed. 20 centimeter cube of steam that was formed. That's answer 1. 20 centimeter cube of steam was formed. That means every single 20 centimeter cube of hydrogen will form 20 centimeter cube of steam. And every single 10 centimeter cube of hydrogen will form 10 centimeter cube of steam. So in essence, therefore, every 20 centimeter cube of hydrogen, of H, will form 20 centimeter cube of steam. And every 10 centimeter cube of oxygen will form steam. Will form steam. This is the answer 1. Because we've got our ratio as 20:10:10. This is H. Okay? This is the O. And this 20 is the steam. 20:10:20. Now they said what gas is SS and by what amount? What gas is SS and by what amount? If you check, you know the gas that is SS already. You know the gas that is already SS. Because 20 centimeter cube of hydrogen will form 20 centimeter cube of steam. In essence, 20. So the one that is SS is the oxygen. Because the hydrogen is already 20, that will form 20. So if you look at very well, you know that the hydrogen is SS. Because if you add the hydrogen to the 20, the steam will be 30. So in essence, you cannot, they did not tell you to look for 20, SS or 30. They say look for the same amount with the product that is being formed from. So in essence, the gas that is SS, answer 2. The gas that is SS is oxygen by 10 centimeter cube. By 10 amount, by 10 centimeter cube. So if you check very well, you will know that we've already gotten the hydrogen as 20. Okay? And the steam too is 20. So they are equal. Now the one that is not available, the one that is SS is the oxygen by 10 centimeter cube. Now, you've gotten to know, still on the Gay-Lussac's law, let's solve a particular one again. A second question on Gay-Lussac's law, okay? They can ask you a different question on Gay-Lussac's law. Now they say, if the pressure of a car tire is 1.8 atmosphere, that's the pressure. If the pressure at 25 degrees centigrade, what will be the pressure if the temperature warms to 37 degrees centigrade? To 37 degrees centigrade. Now let's solve. Okay? The Gay-Lussac's law of combining volume has the formula. We know it's P1 all over T1 equal P2 all over T2. That's temperature. I told you when you're solving temperature, if you like you add 273, that's one part. If you like you leave it, you still give you the same answer. You know, we've gone past that stage where they say you must add it. It's not a must. Because whether you add it or not, you will still get the same answer. Okay? In this case, I will not add. I'll just solve like that. Whether you add it or you don't add it, you still get the same answer. Whether you convert the degree Celsius to Kelvin or you don't convert it, you still get the same answer. Now, they said our first pressure, I told you the first pressure you see becomes your P1, first pressure. The second one becomes your P2. The first volume becomes, the first temperature becomes your T1 and the second temperature becomes your T2. Now, our first pressure there is 1.8. So our P1 is equal to 1.8. Okay, our P1 is 1.8. Our P2, okay, our T1 is 25. degrees centigrade. Okay, then our T2, P2 is not there. They say, what is the pressure? But they give us our T2 as 32 degrees centigrade. Now, the formula says P1 all over T1 equals to P2 all over T2. In essence, it is equal to our P1 is 1.8 all over 25 equal to P2 all over 32. Cross multiplication comes to play. Okay? Cross multiplication comes to do what? Play. Now, if we cross multiply, it will give us, like I said, the cross multiplication, like I said, this 2 times this and this 2 times this. This 2 times this and this 2 times this. So when 1.8 times 32 divide P2 times 25. Are you following? Yes. So, therefore, P2 will be equal to 1.8 times 32 divided by 25. 1.8 times 32 divided by 25. When you calculate this thing, okay, when you make a calculation on this thing, you see your answer come out clearly. 1.8 times 32 divided by 25. Okay, so this is our answer. Now, if you do not add the SI unit, okay, you must have to add the SI unit to the answer they gave. Now, if you check, they say the pressure there is in atmosphere. So when you get your answer, you add atmosphere. If you're looking for temperature and they put degree Kelvin, when you get your answer, you put your degree Kelvin. Now, our answer there became 2.304 atmosphere. Now, if you add this 2.304 to P2, okay, and you divide it by T2, the answer you get here will still be the same thing that you get here. The answer you get here will still be the same thing as you get here. Now, let's make our this thing. Now, they say our P1 is 1.8 divided, that's our P1 1.8 divided by 25. Because our P2 is 2.304 divided by our T2 is 37. Let's see if what we got here is what you will get here. Let's see what we get here is what you will get here. Okay, so let's see if what we get here is still the same thing you will get here. Okay, we said 1.8 divided by 25. It gave us 0.072. Here I gave us 0.072. Let's see if this place 2 is the same thing. The one says 2.304 divided by 37. It still gave us the same thing. 0.072. So in essence, our answer is correct. Okay? 2.304 divided 37. So in essence, our answer is correct. So, the next one is the Dalton's law of partial pressure. Dalton's law of partial pressure. Okay? Dalton's law of partial pressure. Now, if you check, the Dalton's law of partial pressure is the Dalton's law of partial pressure came to play by John Dalton. John Dalton gave us the law in 1802, the same time he brought out the atoms. Okay, it's just a calculation of all the pressures in total. Just a calculation of all the pressures in total. Okay, he said the pressure of one gas, second gas, third gas, fourth gas, you add all of them, is the total of all the pressures. In essence, if I put oxygen, sulfur, and hydrogen in one particular container and exert a pressure on it. Okay, I have to calculate the pressure of hydrogen, calculate the pressure of oxygen, calculate the pressure of sulfur. Calculating all of them together will give me the answer I am looking for. So him using these three gases, he came to realize that every single gas does not have the same pressure. Every gas does not have the same what? Pressure. So if you want to calculate the pressure of all the gases in a container, you must have to calculate them individually, independently, before you get your answer. Now you add all of them together and you get your answer. It's like putting orange, guava, and pawpaw in one particular bucket. For you to make it 3, you must have to count them individually. Pawpaw separate, guava separate, and orange separate. In essence, 3 of them will give you 3 fruits. Okay? That is how John Dalton came to play in his partial pressure. Partial pressure means partial. It is not complete. The pressure is not what? Complete. So now, Dalton's law of partial pressure. It states the total pressure of a mixture of gases is equal to the sum of the partial pressure of the individual component gases. Now, when you add all the gases together, okay, it's going to be equal to when you separate them in counting. In essence, you must have to separate them in counting. Their pressures must be counted separately. When you exert pressure on the gas, and you want to calculate their pressure, you calculate their pressure separately at constant temperature and pressure. When the pressure is kept constant, okay, you calculate the pressure exerted on hydrogen, calculate the pressure exerted on sulfur, calculate the pressure exerted on oxygen. Bring them together, it will give you the total pressure exerted on those gases. Total pressure exerted on tetraoxosulfate 6. Total pressure exerted on the whole gases combined together. Now, what is partial pressure? Partial pressure is the pressure that each gas will exert if it alone occupies the volume of the mixture of this at the same temperature. Is the pressure that each gas will exert if it alone occupies the volume of the mixture of the same temperature. Like I said, in essence, each gas will be calculated separately because they occupy spaces in that particular container. When you put 3 gases together, every gas has occupied its own space. Why? Because he came to realize that all gases do not react at the same pressure. All gases do not react with the same force. All gases do not react with the same mass and density. So that particular partial pressure is the pressure that each gas will exert on its own because it occupies a volume. And when the pressure comes, it increases the temperature. Okay? A temperature, it increases the what? Temperature. Now, every gas do not work on the same temperature and pressure. Some gases work in high temperature, while some gases work in low temperature. So if you want to calculate their pressure, you must have to calculate them individually. And that calculation is called partial pressure. But it's going to be at the same temperature. Because the volume they will occupy will be different volumes. Now, ideal gas. Now, these gases that undergo this Dalton law of partial pressure are called ideal gases. They are called ideal gases. Okay? These gases that undergo Dalton law of partial pressure are called ideal gases. If it's not an ideal gas, it will not undergo partial pressure. It's a theoretical gas composed of many randomly moving point particles that are not subject to interparticular interaction. It said it's a theoretical gas composed of many randomly moving point particles that are not subject to interparticular interactions. They are not subject to, they move anyhow. Okay, they do not interact with others. In essence, the hydrogen gas particle will not interact with the oxygen gas particle. The oxygen gas particle will not interact with the sulfur gas particle. Do you understand? So when these gases that do not interact with other gas particles is called an ideal gas. But they move randomly. They move randomly, but they do not partake, they do not collide with other gas particles. If it's hydrogen, hydrogen will collide with its own hydrogen particles, oxygen will collide with its own oxygen particles. Now, disputing the Dalton's law of partial pressure. Real gases are gases that do not behave ideally. In essence, they do not obey the gas laws. The ideal gases obey the gas laws. Okay? But the real gases do not obey the gas laws. The real gases behave ideally when gases are at low pressure and high temperature. The gas laws are at high pressure and high temperature, or high pressure and low temperature. But these three gases behave ideally at low pressure and high temperature. When the pressure is low, their own temperature becomes high. Remember, if the pressure is high, that is when the temperature becomes high. But these three gases, when the pressure is low, the way they move becomes high. Their movement, their temperature become, their movement becomes faster than when the pressure is high. Okay? Therefore, at this high pressure and low temperature, Dalton's law is not applicable, since the gases are more likely to react and change the pressure of the system. So when this low temperature comes and when the low pressure and high temperature come, the Dalton's law is not applicable. Dalton's law becomes wrong. It becomes wrong. Example of these three gases are hydrogen, oxygen, carbon dioxide, and helium. These three gases are gases that are natural. Gases that are natural. Okay? The hydrogen moves faster at low pressure. When the pressure is low, he moves faster. In essence, when the pressure is low, it has a high temperature of moving. The helium, okay, at high temperature, helium becomes a solid at high temperature. At low temperature, helium becomes a liquid. In essence, when you heat helium, it becomes a solid. So in essence, at that high temperature, at that high pressure, its temperature is low. Why? Because it becomes a solid. And we know that solids, their temperature are low. Take, for example, ice block. The ice block, the temperature is low, it's not high. Okay? So when you heat helium at high temperature, it becomes low. The temperature becomes low when you heat it at high pressure. In essence, the movement of particles at that time is not porotic. It's not fast. They are slow. And Dalton's law tells us how these particles will move fast. So in this way, the Dalton's law of partial pressure is being disputed. Example of helium. When helium is being cooled, it becomes a liquid. When it's being heated, it becomes a solid. And in essence, solids have low temperature at that time. Now, combined gas laws. The combined gas laws are a combination of Avogadro, Gay-Lussac, Boyle's law, and Charles' law. Avogadro, Gay-Lussac, Boyle's law, and Charles, those are the combined gas laws. Okay? It was brought together in 1721. After Boyle's law, after Boyle must have scrutinized the gas laws. Okay? Edwin Chamberlain brought they combined the laws together and made it a combined gas laws. Now, let's know what the combined gas law is. It states that the product of the pressure and volume of a gas per temperature is equal to the constant. Now, the volume talks about Avogadro and Gay-Lussac. The pressure constant talks about Charles, and the temperature at constant talks about the Boyle's law. So these three laws say the product of the pressure and volume of a gas per temperature is equal to the constant. In essence, the pressure and the volume, if you times the pressure and the volume at each temperature, all of them will be equal. In essence, if the pressure increases, the temperature will increase and the volume will increase. That's the combined gas law. If the pressure increases, the temperature will increase and the volume will increase. Mathematically, it's P1 V1 all over T1 equals to P2 V2 all over T2. You know what P1 is? First pressure. You know what V1 is? First volume. You know what T1 is? First temperature. Now, the general gas laws. General. The product of the pressure and the volume of 1 gram molecule of an ideal gas is equal to the product of the absolute temperature of a gas at the universal gas constant. Mole is Avogadro, mole number. Pressure is Charles' law. Ideal gas, the Dalton's law of partial pressure. Temperature is the Boyle's law. These are the 4 laws that came together. And the Avogadro's law and the Gay-Lussac's law of combining volume. The whole laws came together. The general gas laws, all the laws came together to give us the general gas laws. That's why they say the product of the pressure and the volume of 1 gram molecule of an ideal gas is equal to the product of the absolute temperature of the gas and the universal gas constant. Every single gas law falls under the general gas laws. If you check the definitions like I placed them for you, you will know that every single gas law falls under it. Now, the mathematical explanation is still the same as the combined gas laws. The P1 V1 equals to all over T1 equals to P2 V2 all over T2. In essence, all the laws brought together gave us general gas law. The pressure, like I told you, is Charles' law. Volume is the Gay-Lussac's law. Gram molecule is Avogadro's law. Ideal gas is the Dalton's law of partial pressure, and the absolute temperature at every given constant becomes the Gay-Lussac's law of combining volumes. Now, next one is ideal gas law and perfect law. The ideal gas law now states that the pressure, temperature, and volume of a gas are related to each other. They are related. It's the same thing. If the pressure increases, the temperature will increase and the volume will increase. So in essence, they are related. Okay, they are equal to. Pressure is equal to temperature. Temperature is equal to volume. In essence, they are directly proportional. Now the next one is ideal gas equation. PV equals to N root T. The ideal gas equation is gotten from the Boyle's law, Charles' law, and the Avogadro's law. Okay? The Avogadro's law, the universal gas constant, and so on. So we said the PV equals to N root T, where P is the pressure. That's the SI in the Newton meter. V is the volume. N is the number of moles of gas. That's the Avogadro's law number. Rho is the universal gas constant, and T is the temperature. T is the temperature. When we get to gas law 3, we'll solve. Okay? We'll use all these equations in making our solvings. So you just have to follow up. Okay, when we get to gas law 3, we'll solve. That gas law 3 is just all about solving. Using the gas laws to solve the behavior of gases. Using the gas laws to solve problems. Using the gas law to solve equations. Okay? Now, next one is fact about the ideal gas law. It works well at relatively low pressures and relatively high temperature. Every ideal gas works at low pressure and high temperature. Every ideal gas. The second one is, it is affected by temperature, pressure, gas, specific gravity, and gas composition. Now, the ideal gas is affected by the temperature, affected by the pressure, affected by the type of gas, and the composition of those gas molecules. The type of gas, okay? The type of gas, the temperature, the pressure, how is the gas, what is the gas composed of, is affected by it. The hydrogen cannot work as the oxygen and vice versa. The oxygen cannot work as sulfur and vice versa. Remember, the hydrogen is the lightest gas, is the lightest molecule. The oxygen is 16 times heavier than the hydrogen. In essence, the hydrogen cannot work as the oxygen. The gravity of oxygen is 16 times heavier than hydrogen. So in essence, this ideal gas, both of them will not have the same temperature when pressure is being acted upon it. They will not work at the same temperature. Take, for example, if oxygen works at 17 degrees centigrade, hydrogen cannot work at 17 degrees centigrade, even in liquids. Okay, the boiling point of water is 100 degrees. The boiling point of ethanol is 70. So they do not work in the same temperature and pressure. So it affects, all right? It affects, the temperature affects it, okay? The gravity affects it, like I said. Now, the next one is compressibility factor. It's the factor that defines all conditions to which natural gas is normally exposed. Every condition that natural gas is exposed is called compressibility factor. Why? Because gases compress in a container. So when they compress, the compression of oxygen will not be the same compression as hydrogen. Why? Because of their mass. Okay? Their mass determines the volume they occupy. The mass of a gas determines the volume it occupies. So in every condition, the gases will not remain the same. When hydrogen and oxygen is being heated, or when they react together, they give us water. So when they are exposed, their behaviors will not be the same. Oxygen cannot behave like hydrogen. Hydrogen cannot behave like oxygen. Because, like I told you, the molecules of gases do not move on the same speed. Why? Because of their mass. Some molecules are bigger than some molecules. In essence, the oxygen molecules is smaller, is not as heavy as the the hydrogen molecules is not as heavy as oxygen molecules. So in essence, hydrogen molecules will move faster than the oxygen molecules. Why? Because the oxygen molecules have more mass than the hydrogen molecules. Now, there is a law that binds the gas laws. Okay? The whole gas law, there is a law that binds it. The law states, because of the compressibility factor, the law states that when the temperature increases, when the pressure increases, the temperature increases and vice versa. When the pressure increases, the temperature increases and vice versa. In essence, if the temperature increases, the pressure will increase. If the pressure increases, the temperature will increase. We've come to the end of this lesson, but before we go, I think we should use our exam guide in sorting ourselves out, okay, to know what we have learned today. Now, we'll go to 2001. Now, we've gone to the end of this section, but before we leave, we should be able to use our exam guide to quantify what we have learned, as we always do. 2001, question 13. Question 13 says, P is equal to P1 plus P2 plus P3. Where P is the total. Where P is total. Where P total, sorry, is the pressure of a mixture of gases. This equation above is an expression of, I told you that when you combine the whole pressure together, when you want to calculate a pressure of a gas that comprises of 2 or 3 gases, okay, you must have to calculate their pressures individually. When you get the pressures individually, you now add them together to give you the total pressure of that particular gas. And in essence, that is the Graham's law. That is the Dalton's law of partial pressure. That is the Dalton's law of partial pressure. The Dalton's law of partial pressure, like I said, the mathematical formula is P1 plus P2 plus P3 gives you P total. Gives you P total. That's the law of partial pressure. The P1, the first pressure of first gas, the second pressure of second gas, third pressure of third gas gives you the total number, the total pressure of all the gases. In essence, it is 1 plus 1 plus 1 equals to 3. It will be 1 plus 1 plus 1 equals to what? 3. So that is the answer. So the answer there is the Dalton's law. Thank you for participating in today's class. You can practice more questions using the Exam Guide app. The app scores and gives a detailed explanation of all the questions at the end of your practice test. You can learn a particular topic of interest with different modes like study mode, mock mode, and practice mode. It also has other features that make learning fun. It is a must-have for all serious students. Download from www.examguide.com if you don't have it yet. See you in the next class. Don't forget to subscribe to our channel. hit the notification bell, and share the videos to people that will benefit from it. Bye.